Hi there everyone, and welcome back to the exam countdown from TheMathsTutor.ie. So as you can see, this week we're going to have a look at statistics, and in particular the inferential statistics. So that's a new topic that was brought onto the Leaving Cert course in around 2015. So it's relatively new, and it is something that continues to appear on paper 2 most years. Okay, so you'll see, as always, I have linked 2 very good videos in the chat there. The first one will go through p-values in a little bit more detail, so we will be touching on them today, but the video just goes through it in a little bit more detail. And the second one looks at an exam question from 2019, question 8, one of the longer questions that year. So first of all, just a quick introduction, I suppose, to what inferential statistics is. So I want you to imagine that we have a population of people, and we basically want to find something out about those people. So we want to do some sort of a survey to maybe, for example, find out their average height. Okay, so what we do, because it's less time consuming, is we basically take a little sample from that population. So it's a smaller group of people, and it's less time consuming, and it's much easier to get results from a sample. And what we do, once we get our results from the sample, we take those results and we make conclusions, or we make inferences. So a conclusion or an inference is basically the same thing. So we make conclusions or inferences about the population, hence where the name inferential statistics comes from. Okay, so we use our sample, we use the data from the sample to make conclusions about the population. And sometimes those conclusions are right, sometimes they're wrong, and often we have to test those conclusions or those hypotheses as well. Okay, you'll notice down here, I've just very briefly gone through, I suppose, the main things that we need to be able to do in inferential statistics. So that first one there is our normal distribution and using our Z tables. So we'll have a look at the Z tables in a second, but you'll be familiar with this normal curve from your studies of inferential statistics. And you should also be quite familiar with these critical values, minus 1.96 and plus 1.96, which we'll see in a couple of the exam questions in a second. And we know from our studies that inside, so within 1.96 standard deviations of the mean, we have 95% of the data lies in there. And again, that's coming from our log tables. And then we also know from that if 95% of the data lies within 1.96 standard deviations of the mean, then outside here in these blue parts, we have our 5%. So that's coming from 100% minus the 95%. So those two values, plus and minus 1.96, those are our critical values, and you'll be seeing those quite a bit in inferential statistics. Okay, so like I said, the first thing we need to be able to do is to understand that normal distribution and use the Z table. So I'm just going to scroll across here to 2 pages from your log tables. Sorry, that should be coming up there. 2 pages from your log tables that you should be quite familiar with, page 36 and 37. So again, you'll see your normal distribution up there at the top, and we're familiar with 36 and 37 giving us the probabilities for the normal distribution. So make sure that we understand that your log tables will only ever work to the left of a particular Z value, and you will notice your Z values, so that's these ones around the border here on both pages, they're always only positive Z values. So we have a little bit of work to do if it's a negative Z value we're dealing with. Okay, just to come back up here then. So that's the first thing we need to be able to do in inferential statistics. The second thing we need to be able to do is use confidence intervals and create confidence intervals. Both so for number 2 here, we need to be able to do a confidence interval for the mean and a confidence interval for, not the population, for a proportion. Okay, so I'm just going to write out our formulas here very, very quickly. You'll see we'll be using them in some of the exam questions later on anyway. But your confidence interval for your mean, so you have mu, which is your population mean, and the interval on the right hand side, it's our x bar, so that's our sample mean, plus 1.96, so we're seeing that critical value here, plus 1.96 standard errors of the mean, so that's our sigma over root n, and we have exactly the same on the opposite side except minus 1.96. So just two things to say to you there. First of all, this sigma over root n, that's basically our standard error of the mean. You're going to find that on page 34 of your log tables. Right there is your standard error of the mean. And the second thing to say to you with this one is the reason it's plus or minus 1.96 is because it's a 95% confidence interval that we'll be asked to find, okay? And it's the 95% confidence level is the only level that we work at for Leaving Cert higher level maths. So we don't need to worry about any other confidence levels. Your confidence interval for a proportion then, similar structure. You have P, the population proportion in the middle, and either side then we have P hat, which is your sample proportion, plus 1.96 again, but this time it's going to be the standard error of the proportion. So if we go back up to page 34 of our log tables, down at the very bottom we have the standard error of the proportion. So don't get confused. If the question says mean and it's a confidence interval for a mean, it's the standard error of the mean we use. If the question mentions a proportion, it's the standard error of the proportion that we're using. So it's 1 plus or minus 1.96. This time it's standard errors of the proportion. So that was P, square root of P times 1 minus P over N. And sorry, that square root should be around the whole thing. And similarly on the opposite side, the only difference is it's minus 1.96 this time. And just the one thing to mention there with this one is you'll often see that in your standard error of your proportion, you don't know P in the question. So normally we actually substitute P hat in there instead. Because normally this P in the center, that's normally not given in a question. That's normally not known. Okay, so that was our confidence intervals, that second part there. Our third part is hypothesis testing. Hypothesis testing. That's the third thing we need to be able to do. So we'll go through that in an exam question later on. And the last thing is p-values. Okay, so quite often p-values are something some students struggle to get their head around, but I'm going to hopefully show you a nice easy way of using p-values and interpreting them. And as I said, that very good video in the chat, that first one in the chat there, also does a very good job of explaining the use and the interpretation of p-values. Okay, so let's have a look at an exam question. We're going to start quite recently, so we're going to start with the 2021 Paper 2, question 8. And before we do, actually, sorry, there's two formulae that I forgot to mention that we also use. Page 34, you will see this formula, which is our standardizing formula. So hopefully you can see that there. That is basically used for converting to standard units. Okay, so if we need to convert to standard units in order to use pages 36 and 37 of our log tables, that's going to be the formula that we will use. And secondly, in hypothesis testing, so top of page 35 we have our one sample Z test formula that you're going to see quite a bit of as well. So you don't need to remember any of those formulae, but you do need to remember what each of the symbols stand for. Okay, so let's go straight then to 2021. It's paper 2, as inferential statistics and statistics in general always is, and this is question 8 that we're starting with. So in a school, all first years sat a common maths exam. The results in integer values were normally distributed, so that's important because we can use our log tables, with a mean of 176 marks and a standard deviation of 36 marks. The top 10% of students go forward to a county maths competition. Find the minimum mark needed on the exam to progress to county stage. Okay, so the first thing I'm going to do here is, because they told me my results were normally distributed, it's a really, really good idea to actually draw your normal distribution and mark in on it exactly what's going on here. Okay, so we're told the top 10%, so I'm going to mark in the top 10%, roughly around there. It doesn't need to be perfect, but basically 10% up there. So that means that to the left, because our log tables will always work to the left, there's going to be 90% to the left, okay? And the mean is 176, so we know that the mean is always bang in the middle there. So we're basically trying to figure out what this value here is. We're going to use our Z tables, page 36 and 37 of your log tables. We're going to use those first to figure out what this value is as a Z value. And then we're going to use our formula from page 34, which is our standardizing formula, to try figure out what the actual value is. So remember, the reason you're using your Z tables and your log tables is because you're looking for a standard unit, and then we can use this formula to change from our standard units back to whatever units are in the question. In this case, it's marks in a maths exam, okay? So because our log tables only read to the left, we're going to look for the Z value corresponding to 90%. So we're going back to page 35 and 36 of your log tables, and you're going to look for the closest value there to 90%. Okay, so you're looking around close to 90%. We're talking about 1.28. Okay, so I think that's the closest value you're going to get to 90%. So the Z value corresponding to that is 1.2. Let me just show you in a different color. There's our Z value, there's our probability value. Z value corresponding to that is 1.28. Okay, so what we've just figured out is that the Z value of this point here, at which 10% of them are above that point and 90% below, the Z value is 1.28. So I'm going to go back to my formula. I know what Z is, so I have Z. I know what my mean is, so my mean is mu, 176, and I know what sigma is, so my sigma is 36. And not a bad idea at all to actually mark those in. So this is my mu, that's the mean, and this is my sigma, that's my standard deviation. So I'm just going to plug into the formula. My Z is plus 1.28, and I know it's plus 1.28 because of where it's positioned on the normal curve. X is what I'm looking for, minus 176, and we're dividing by the 36, the sigma. Okay, so it's up to us to manipulate that formula, and we're trying to get that X on its own. So when we do that, we should be getting X is equal to 222.08. Okay, and what we're doing there is we're rounding up that value. We're rounding that value up to 223 marks in this case. Okay, so again, we're basically looking for your Z value first, and we found that by using our log tables, our page 36 and 37, and then we used our standardizing formula to change that back into marks in this case. Okay. Part 2. The school awarded a certificate of merit to any student who achieved between 165 marks and 210 marks. Find the percentage of first years who received the certificate of merit. So again, I'm just going to draw my normal distribution. I'm going to mark in my 165 and my 210. So remember, your mean was your 176, and that's always in the center. So 165 is somewhere to the left of that, and 210 is somewhere to the right of it. And what we're trying to find is we're trying to find the percentage of the students in there in the shaded part. So in order for us to use our log tables, we need to basically figure out, these are our X values if you like, we need to change those to Z values, and we're going to do that using our standardizing formula from page 34. So I'm going to start with 165, and I'm going to figure out the Z value for that. So it's 165 minus my mu from the previous part was 176 and my sigma from the previous part was 36. We plug that into our calculator. We were expecting a negative value because look where it is. It's to the left of the mean. Minus 0.31 is what we should get. We're going to do exactly the same, but this time 210 is my x value, 176 is my mu, and 36 is my sigma. And this time we're expecting a positive value because look where it is. It's over to the right of the mean. So it's 0.94. Okay. So our job is to first of all work out the probability to the left of 0.94, and that'll give me all the way over to here. Okay, so if I just even shade that in red for you, just to show you a little bit clearer. And then once we find that, we're then going to find the probability to the left of minus 0.31. So I'll show you that in pink. And if we subtract one from the other, what we're ending up with is this yellow part in here. So if we have the red, what I've shaded in red, minus what I've shaded in pink, that'll leave you with the yellow, which is exactly what you want. So we're going to find the probability that Z is less than or equal to 0.94. And from that, we're going to subtract. So let's try keep with the same colors, roughly, if we can. From that, we'll use a pink here. We're going to subtract the probability that Z is less than or equal to minus 0.31. So the pink part there. This can be read straight from your log tables. So you're going to go to 0.94. Let me just show you here very quickly. We're going to go to 0.94. So there's 0.9. There's my 0.4. And when we read in, we're getting 0.8264. So let's go back here and write that in. That's 0.8264. This part, so because it's negative, what we need to do is we need to look for 0.31, find the probability of that, but then we need to subtract it from 1 because it's a negative value. So let's go back to our log tables. Let's look up 0.31 because our log tables will only deal with positive values. So there's my 0.3, there's my 0.31, so that's 0.6217. Okay, so lots of flicking back and forth here, but hopefully you can keep up with me. So it's going to be minus, and this works out to be 1 minus 0.6217. Okay, again, we're subtracting it from 1 because it's a negative Z value. This whole part can be thrown straight into your calculator, and that should give you the yellow shaded part on my normal distribution. You should end up getting 0.4481, but as they asked for the percentage of first years, that's going to be 44.81%. Okay, so again, a little bit of work with your normal distribution there, which is quite popular in exam questions. Part 2. The school awarded, a news report claimed that 6th-year students in Ireland studied an average of 21 hours per week outside of class time. A Leaving Cert class surveyed 60 students in 6th years. I'm just going to highlight all of the numbers in the question, chosen at random from different schools. It found that the average study time was 19.8 hours and the standard deviation was 5.2 hours. So we're asked to find the test statistic, in other words, the Z score of this sample mean. So let's name all of the numbers that we have in our question. So the standard deviation, that's always going to be my sigma. The 60 students, that's my sample size. The 19.8 is the sample mean, so that's X bar. How do I know it's the sample mean? Because we surveyed 60 students, so there's my sample size, and their average study time was 19.8. So that's the average of the sample. So that must mean that mu, my population mean, in this case, is 21 hours. And that's what the newspaper is claiming is the mean for all 6th-year students. So we're going to use our formula from page 35 of your log tables. That's your Z test formula, or the Z score. Z is equal to X bar minus mu divided by sigma over root n. And it's a matter here of just subbing in your numbers. So it's going to be 19.8 minus 21, and we're dividing by sigma, which is 5.2, over root n, which is root 60. So you might notice that this part that we have here is actually your standard error of the mean. And if you want to put that into the calculator first, you can go ahead with that. Okay, and what you're ending up getting is a z-score of minus 1.79. So if this was a hypothesis test, let's think about what we would do. There's my normal distribution, there's my minus 1.96, and there's my plus 1.96. Look where minus 1.79 is. Okay, so minus 1.79 actually lies somewhere in here. I don't really care how far in, but all I care is that it's actually lying in there. So if it was in here, which it is, we would accept, or fail to reject is the correct language, we would fail to reject our null hypothesis if this was a hypothesis test. In this case, it's not. Okay, so part 2. Find the p-value of this test statistic and comment on what can be concluded from its value in a two-tailed hypothesis test at the 5% level of significance. So the 5% level of significance is exactly the same thing as the examiner mentioning a 95% confidence level. It means exactly the same thing. So what's our p-value? Well, I want you to imagine again your normal distribution with again your critical values, plus and minus 1.96, okay? And what your p-value is, once you find your z-score, okay, and just say, for example, it's not in this question, but just say, for example, your z-score was, we'll just say minus 2.5, okay? So that would lie out here somewhere. And if we know it's symmetrical, so if we put in plus 2.5, that would lie up here somewhere, okay? What your p-value does is it basically calculates the shaded area to the left of minus 2.5 and to the right of plus 2.5, if that's your z value, okay? And what you do, once you calculate that shaded area, you compare it then to 5%. Where's the 5% coming from? Well, the 5% would be all of that to the left of minus 1.96 and to the right of plus 1.96. Okay, and you compare it to that 5%. And if your p-value is less than 5%, you basically reject or fail to accept your null hypothesis. If the p-value is bigger than 5%, well then you're back kind of in here, into this territory in here, which is your accept or your fail to reject territory. So you're accepting your null hypothesis. Okay, so we're going to calculate the p-value of this test statistic that we found up in part 2. And how we do that is your p-value formula is twice, because there's 2 of them, there's 1, there's the second, twice 1 minus the probability that z is less than or equal to whatever your test statistic is. Okay, so in this case, that's going to be twice, so 2 times 1 minus the probability that z is less than or equal to this value that we found up here, but we always take the positive of it because our log tables, page 36 and 37, they only deal with positive z values. Okay, so that's our formula for p-values, and that is one that needs to be remembered because it's not in your log tables. This part, we can look that up straight from our log tables. So let's go back to 1.79. Back up here in our log tables, we'll change the color so we can keep it nice and clear. So we're looking for 1.79. There's our 1.7, there's our 0.09. So it looks like we are getting right to here, 0.9633. Okay. So back to our question. It's going to be 2 times 1 minus, and we've just worked this part out to be 0.9633. That can go straight into your calculator and you're ending up with 0.0734, which as a percentage is 7.34%. Okay, what's our conclusion in relation to the news report claim? So basically, our 7.34%, that's a little bit bigger. Don't care how much bigger it is. All I care is that it's bigger. It's bigger than 7.34%. And because it's bigger, that means I'm heading in here. I'm back into my, what I like to call my accept, or better language is fail to reject region. Okay, so my conclusion is, since 7.34% is greater than that very important 5%, okay, because remember, to the left of minus 1.96 plus to the right of plus 1.96, we have 5%. So since it's bigger than 5%, then what we say is the result is not significant. So what do I mean by the result and it's not significant? Let's go back up here and remind ourselves what the question asked. Okay, so let's scroll back up here. Basically, this news report claimed that students spent 21 hours per week outside of class time studying. But then when we went and we did our survey of the 60 students, the randomly chosen survey, or the randomly chosen sample, their average study time was 19.8 hours, which is a little bit of a difference from 21 hours, okay? But what we're saying, with our p-value, we're saying, well, the probability, so p-value stands for probability value, the probability that the result is 19.8 by pure chance, just by pure potluck. We picked these 60 students and by pure chance, their results were slightly different. The probability of that being by pure chance is 7.34%. In other words, there's not something going on to say that the newspaper's claim is wrong. You're allowed a little bit of a margin of error. So this is not a significant result because it's bigger than 5%. And it's because it's bigger than 5% that's why we still accept what the newspaper is saying. Okay, so it's not significant. And therefore, we can conclude that the average time spent studying outside of class time by these Leaving Cert students, so it's quite long-winded, but we need to give our conclusion in relation to the news report claim, or often the question will say in the context of the question. So we can conclude that the average time spent studying outside of class time by Leaving Cert students is in fact 21 hours. In other words, we're accepting that what the newspaper said is right. We're accepting, or we're failing to reject, the null hypothesis, if you like. Okay? And why? Well, because our p-value was a little bit bigger than 5%. And I don't care if it's 5.1%, we still accept. In that case, the result is not significant. Okay? If the result was smaller than 5%, well, then we're out here. We're out in these critical regions, if you like. We're less than 1.96, or we're greater than plus 1.96. So we're out there in those critical regions. For example, if it was 3%, there's a 3% chance or 3% probability that the result was different by pure chance. And it's because that's so small that the result then is significant. And there must be something happening to say that we're getting a different result. Okay? Something that might help you to remember your conclusion is this little rhyme. So if P is low, in other words, lower than 5%, then what we say is HO, which is your null hypothesis, HO must go. Okay, and if P is high, so if it's bigger than 5%, then we say HO can fly. So in other words, go ahead with your HO, with your null hypothesis. So if P is low, HO must go. And just a reminder there, your HO is your null hypothesis. Okay, now we didn't get a chance to do a hypothesis test here. But like I said, I have videos linked in the chat there from the 2019 paper 2. So your null hypothesis and your alternative hypothesis, something again that people have a little bit of trouble with, okay? I would always say that your null hypothesis, your HO, is always your status quo, if you like. Everything is as it should be. Everything is as normal. There's no change, no difference, no effect. Okay, so for example, has there been a change in the mean time or the average time spent by students studying? No, your null hypothesis is there's no change. Is a drug or a vaccine for a virus, is it having an effect? Your null hypothesis is no, it's not having an effect. Is a new machine having an effect on the mean length of nails being produced? No, your null hypothesis is having no effect. There's no difference and there's no change. Okay, so like I said, now we've just got through one question there, but I think it's quite important not to rush this. So we've gone through a little bit of using the z-scores, using the log tables, reading those page 36 and 37. We've done a little bit on standardizing. Okay, so standardizing units. We've done the z-score. And we've done the p-value, which is becoming a little bit more popular every year in inferential statistics. We didn't quite get to the mean confidence interval for the mean or the proportion, but any of our full members there, you have loads and loads of videos to help you get through that as well. Okay, thanks for tuning in, guys.